We're now going to look at the family of alkanes. Alkanes are what are called the saturated hydrocarbons, meaning they have as many hydrogens on the carbons as is possible, and they have no functional group. If you have a compound that has no ring, so that means that the carbons are attached one to the other in a chain that does not lap back on itself, then they are called acyclic. The alkanes are acyclic. Because hydrogens are put on carbons until carbons have 4 bonds, we know how many hydrogens are on each carbon in a particular compound by looking to see what else is attached to the carbon. For instance, if a carbon has only one other carbon attached to it, then it must have 3 hydrogens on it. If a carbon has 2 other carbons attached to it, well then it must have 2 hydrogens on it. If a carbon has 3 carbons attached to it, then there is only 1 hydrogen. And if a carbon has 4 carbons attached to it, there are no hydrogens on it. This regular behavior that we see with the number of hydrogens on a carbon in an alkane gives us a general formula of CnH2n plus 2. N is the number of carbons in that chain, and 2n plus 2 is the number of hydrogens. So if I have pentane, which has 5 carbons in it, then the number of hydrogens is going to be 2 times 5 plus 2, or 12. So I know just when I say 5 carbons in an alkane, I know that the general formula has to be C5H12. When there is a cycloalkane, that means one end of the chain has come around and bound to the other end of the chain. It forms a ring. These are called cycloalkanes, cyclo meaning in a ring. When one end comes and forms a bond with the other end, 2 hydrogens must be removed. This means that the general formula for any cycloalkane is CnH2n. So cyclopentane, which has 5 carbons, must have 10 hydrogens on it, 2 hydrogens on each carbon. So the general formula for cyclopentane is C5H10.
Now, there's some characteristics that all alkanes have, and all alkanes we will find are oily or hydrophobic. This means that they are not water-soluble, they are nonpolar. They will be dissolved by nonpolar compounds, but they will not dissolve in water. Typically, for their molar mass, alkanes have low melting points and low boiling points. Now, if you increase the molar mass, you will have the boiling point and melting point increase. So if I look at something like C8H, let's see, that would be 18, then what you get is something that has a relatively low boiling point for its molar mass, probably a boiling point of around 40 degrees or Celsius. But if I look at something like C40H82, well, it would have a very high boiling point because it has such a large molar mass. And comparing those two compounds, really you know characteristics of those compounds, because octane is a component of gasoline, and you know it's very volatile. And something with 40 carbons in it might be an alkane with 40 carbons in it, might be a component of motor oil, and you can see the difference in the characteristics. Any portions of molecules that look like alkanes, that means their carbon-carbon bonds and carbon-hydrogen bonds are going to be hydrophobic and will resist solution in water. So keep that in mind when we start looking at molecules that have different functional groups on them. Remember that the parts that look like alkanes are hydrophobic and will resist being pulled into water. Carbons can make chains, as we've been talking about, and you can see I'm showing just a few different lengths of chains. This is what makes organic chemistry so interesting, because carbon is very flexible. The chains all have names telling you how many carbons are in there. So right here I've shown you the prefix that tells you how many carbons are in a particular chain. And so if we have meth, it tells us 1 carbon. Eth, it tells us 2, all the way down to something like hept or dec, which are telling us 7 and 10. And you do need to know these prefixes. In the future, we will be using them to name compounds. Now, remember that in the alkanes, the only thing that we have are carbon-carbon single bonds, and then hydrogen surrounds the carbons until there are 4 bonds on the carbons. So if you look at this, methane, meth says 1 carbon, and then the ane ending tells you it's in the alkane family. So it must have 4 bonds altogether, and anything that is not having 4 bonds has to have hydrogens completing the 4 bonds. So methane has the structure of 1 carbon and 4 hydrogens surrounding it. Ethane has a similar structure but 2 carbons, and you can see the formula for ethane. Propane, prop says 3, ane says all carbon single bonds and hydrogens surrounding it to make 4 bonds on carbon, and so we come up with this structure. Notice I'm drawing both the structural formula and the condensed formula. Now, on the carbons, we can have attachments. When we have attachments on a carbon, we call it a substituent. They can be other carbon chains. For instance, you might have 4 carbons in a row that we would call bute, and to the second carbon, you might have 1 carbon attached. We call that attachment, we name it with that meth for 1 carbon for that attachment. These attachments are also called branches when they're all carbon chains. The most common way to call them are alkyl groups, and that comes from alk being for alkane and il meaning attached. So alkyl group means it's an alkyl type carbon chain, an alkane type carbon chain, and il means it's attached. Now you can have heteroatom substituents, but we will look at that later on. Okay, the chains are numbered to place the substituents. So when we talk to each other and we describe a molecule with the name, then the other person can be able to reproduce that structure. So the way that we do this is we always find in the compound the longest chain. Once we find the longest chain, we pick the prefix that tells you how many carbons are in that longest chain. And then we end the prefix with the suffix that tells us what group it's in. The alkanes have no functional groups. They're all carbon-carbon single bonds with hydrogens, and so we end all of those compounds with the ending ane. We count from the end to the substituent. We count from the end that will give us the lowest possible numbers. Each substituent then gets a number from that one numbering system. You never switch numbering systems in the name of in the process of naming a compound. You identify your numbering system and leave it there. And then when you go to name the compound, in front of this part of the name that you got from the longest chain, you then will put your substituent names and put numbers placing them on the chain. And this is probably very confusing to you. It's much more straightforward to see an example. Let's look at an example now. You can see that this is an alkane because it's all carbon single bonds, and then hydrogen surrounding the carbon. The longest chain that you see is 5 carbons, so that gives us the pent on the as the prefix in the name that you can see down there in pink. Because it is an alkane, no functional groups, only carbon single bonds and hydrogen surrounding the carbons, then we know it has an ane ending because it's in the alkane family. So this is pentane. But if we look at what is not in the longest chain, I have circled there a 1 carbon attachment. That's called a substituent or a branch. That attachment has 1 carbon in it, so we give it the meth prefix. Because it's attached, we give it an -il ending. So that group that is attached to the 5 carbon chain is called methyl. Now, what we do is we can count from either end of the chain. I can count from the left end of the chain, and I go 1, 2, 3, 4 to see where the methyl group is attached. Or I can count from the right end of the chain, 1, 2, and find the methyl attached. 2 is the lower number, so we choose that. So what you need to realize is you always count the carbons in the longest chain. It's not always going to be written out straight. Sometimes it will have little kinks in it, so be careful. If you draw a line through that longest chain, you will see the substituents more easily. Count the number of carbons, and that gives you the prefix. When you see there's no functional groups besides carbon single bonds and hydrogens on the carbon, then you give it the ane ending. You name all the substituents and you list them in alphabetical order in front of the alkane name, and then you number their place on the chain, making sure you have the lowest numbering system, and don't switch numbers. It's one system. You can't number from one end and then number from the other. If you ever have more than one of a particular type substituent, for instance, if you have 2 1-carbon chains, then you use prefixes like di or tri. So if you have 2 methyls attached to an 8-carbon chain, it would be dimethyl octane. Here are some common prefixes, and you can see they all follow that same prefix system that we have been introduced to. 1 carbon is meth, plus the ending -il says attached. 2 carbons, F, -il says attached. 3 carbons, prop, -il says attached. 4 carbons, bute, -il says attached. Now notice I have a little line attached coming off the carbon to show that it's attached to something. And also notice that the carbon that is attached to the chain has 1 less hydrogen to allow it to be attached to the chain. So in the ethyl, the carbon that is attached to the chain has only 2 hydrogens attached to it, plus 1 carbon, because it has to leave that 4th position for attachment to the chain. But the end of the chain, the ethyl chain, the end of the ethyl substituent, is attached to that carbon, 1 bond, and then 3 hydrogens attached to make it 4 bonds overall. Any length carbon chain can be a substituent. All you have to do is count the carbons. If you find them to be 8, well, then that's oct, and then you add the -il ending. So now what I want you to do is look at these examples here, find the longest chain, identify the substituents, and then number them in the chain. Notice in the first one I'm using a condensed formula, and in the second one I'm using the structural or skeletal or shorthand formula. Make sure you look for the longest chain even if it is kinked. To do this first problem, you see that there are 5 carbons in the longest chain, so I name it pentane. Then I see that attached to that longest chain are 2 methyl groups. Put in dimethyl. Now I have to number where they are. If I number from the left, I would get 1, 2, 3, 4 dimethyl. If I number from the right, I would see that it is 2, 3 dimethyl. So I choose the lowest number system and I get 2, 3 dimethyl pentane. On this bottom structure, finding the longest chain is a little bit more difficult because it's kinked. The longest chain is not hexane. Instead is this part of the molecule, which has 1, 2, 3, 4, 5, 6, 7, 8 carbons in it. That gives me the prefix oct, so I octane. Now I see that there are 2 substituents attached, of course, to the same carbon there. And so I'm going to call them ethyl because there's 2 carbons in one attachment, and methyl, 1 carbon in the attachment. I can number the system either from the bottom, which would be 1, 2, 3, 4, 5, 5 ethyl methyl, or I can number it from the top, which would be 1, 2, 3, 4, 4. So I'm going to choose from the top because that's the lowest numbers. And remember, you list your substituents in alphabetical order, so we do 4 ethyl, 4 methyl octane.